Before we dive into solving problems related to the definition and types of functions, let's take a moment to clearly understand the basic properties of a function. Let's start by plotting some random lines or points on an xy coordinate plane. These are what we call relations. They show how x and y are related. But out of all possible relations, we focus on a very specific kind called a function. In fact, much of what happens in the world around us can be described using functions. For example, let's say you recorded your weight every morning for an entire year. Now imagine plotting this data on a graph. Let the x-axis represent the day from 1 to 365, and the y-axis represent your weight each morning. Each day, you step on the scale and see one number, one output. That's exactly what a function is. For every single input, there is exactly one output. With this graph, you can analyze your data in many ways. You could find the highest weight, the lowest, the average, or see where your weight changed the most. Later in your studies, you'll see how all of this connects to calculus, especially concepts like derivatives. Now, let's look at a few different graphs. Can you find which of these are functions? Let's check whether each graph is a function, and let's also identify the domain and the range. Here's a quick trick. Use the vertical line test. If a vertical line touches the graph at more than one point, it's not a function. Why? Because it would mean one input, x, has more than one output, y. We can see that all 6 graphs qualify as functions. So let's go through them one by one and check their domains and ranges. First, y equals x. It passes the vertical line test, so it is a function. The domain is all real numbers and the range is all real numbers. Next, y equals x squared. It also passes the vertical line test, so it is a function. The domain is all real numbers, but the range is all real numbers greater than or equal to 0. Now, consider y equals 1 over x. It passes the vertical line test, so it is a function. But what happens when x equals 0? Don't worry, when we write y equals 1 over x, the condition x is not equal to 0 is always implied. So the domain is all real numbers except 0, and the range is also all real numbers except 0. In this graph, both the x-axis and the y-axis are called asymptotes. An asymptote is a line that a graph of a function approaches but never actually touches, as the input or output values go to infinity or negative infinity. Next, y equals 2 to the power of x. It passes the vertical line test, so it is a function. The domain is all real numbers and the range is all real numbers greater than 0. Now, y equals the square root of x. It passes the vertical line test, so it is a function. The domain is all real numbers greater than or equal to 0, and the range is also all real numbers greater than or equal to 0. Finally, y equals the absolute value of x. It passes the vertical line test, so it is a function. The domain is all real numbers and the range is all real numbers greater than or equal to 0. Now, among all these functions, notice that 2 graphs are different. Y equals x squared and y equals the absolute value of x. They pass the vertical line test, so they are functions. But both of them fail the horizontal line test. Any horizontal line above the x-axis will touch the graph in 2 places. Except for these 2 graphs, all the other functions satisfy the condition. When x1 is not equal to x2, then fx1 is not equal to fx2. These are called one-to-one functions. That means different inputs always give different outputs. But there's a special case of one-to-one functions called one-to-one correspondence, also known as a bijective function. This happens when the range and the codomain are exactly the same. In other words, every output value is used and used only once. Let me give you an example. Imagine there are 5 students and 6 different gifts. If each student picks one unique gift, one gift is left over. This is still a one-to-one function because no 2 students picked the same gift. But if there were exactly 5 students and 5 gifts, and each student picked one, then every student and every gift are perfectly matched. This is one-to-one correspondence. What's special about one-to-one correspondence? You can work backwards. If you know the gift, you can figure out which student chose it. And that's the idea behind an inverse function, switching the input and output and still being able to find the original value. Let's look at 2 more graphs. First, the graph of y equals sine x. It passes the vertical line test, so it is a function. However, any horizontal line will intersect the graph infinitely many times in a periodic pattern. That's why this is called a periodic function. The domain is all real numbers and the range is from -1 up to +1. Finally, consider the equation x squared plus y squared equals 1, the graph of a circle. Here, a vertical line may touch the circle at 2 different y values, so this is not a function, it is simply a relation or an equation. Let's wrap everything up. First, we have relations. Inside relations, we have a more specific set called functions. Within functions, we have one-to-one functions. And inside those, we find the most specific case, one-to-one correspondence. One-to-one correspondence means that an inverse function exists, and many exam problems are built around using these relationships.